Welcome to More About Stats. Thank you for joining me. We're going to look at standard normal here, and we're actually going to go through the process of how to figure out what the z-score is, or what that standard normal value would be. And this is exactly the formula that you would use right here. X is the actual height, mu is the mean, and then this lowercase sigma is standard deviation. Here we are talking about this mu, and the standard deviation is these two values right here as being found values. So they are based upon a data set, a rather large data set, hopefully, that is of information that we've collected over a long period of time. And here what we're looking at is women's height is the actual problem. So how does that fit in? X is the actual height. So we have a particular individual, and we want to see where this individual or individuals fit in with the rest of the population in terms of how common is that, or what percentage of the population is above that or below that, and is that quote unquote a normal value. And when we say normal, we're not attaching any positive or negative connotations to that. We're strictly looking at whether we are dealing with values within one standard deviation, if you will. Okay, so don't read too much into that notation when we start saying that. So let's just say that we're talking about we have an actual or a particular person who has a height of 70 inches, and we want to compare that against a individual who has a height of 60 inches. Okay, so 70 inches is 5 feet 10 inches. Because you got 5 times 12, which gives you 60, plus 10 more gives you 70. So, and then you're comparing that against someone who is exactly 5 feet tall. Okay, now how do these two individuals match up? We have our mu value here of 64.2, okay, inches, which means that they've done their data collection, and the data collection has shown that the average height for a woman is 64.2 inches tall, or that would be 5 feet 4.2 inches. And then we have the standard deviation here of 2.8 inches, meaning one standard deviation in either direction. So 2.8 to 64.8 would give you 67. It would be one standard deviation. We'd add on there, and that would be one standard deviation in that direction, one standard deviation in the other direction. Now we can do that. We can definitely add standard deviations to this to figure out how far do we have to go to get to 60 or how to get to 70, and that can tell us a lot of information there. But we can also use this formula here when we standardize this, because then we can also do the exact same process with the male population, which would have a different mean and a different standard deviation, and we can see how 5'10" or 70 inches compared within the male population versus 70 inches within the female population. It actually allows us to talk about those values very directly instead of indirectly. So here we would say, let's go ahead and call this z-score for the first individual. We'll call this x sub 1. We'll call this x sub 2, just to make it a little bit easier to keep track of the values. So this would be z sub 1, and we'd find that by doing 70 minus our mean of 64.2 divided by our standard deviation of 2.8. And when we do that, we end up with 2.0, strike that, not 0, 2.07. Yeah, there we go. Okay, and with Z2, we do that process there, and we end up doing 60 minus 64.2 all over 2.8. And when we do that, we get negative 1.50. And I do encourage you to go out 2 decimal places as a standard rule, because you will run into situations where that second decimal, that hundredth spot, is extremely useful to us. So what does this mean? It means that someone who is 70 inches tall is more than 2 standard deviations outside of the mean. So how is that information useful to us? Well, let me just kind of draw out my bell curve here. Not exactly a good or great bell curve, but it'll do. And we know that one standard deviation this way, -1, and 2, of course, here is mu, right? So, no, this isn't 2. This is 1 in this way. And then we'd have 2 right there. And over here, we'd have -2. And then we'd have -3 and 3. And, of course, we're saying this is our z curve, or our standard normal, okay? Not just normal, but our standard normal, because a normal curve is your basic bell shape. It has the same criteria as a standard normal shape in that this is 34.1-ish. This should, of course, be 13 and some change, right? So 13 in a little bit, and this is 2 in a little bit. I think this is 13.4 right there. And then we have the same thing on the other side, right? So we have those values that, so 13.6, pardon me. And then on the same thing on the other side, it's 34.1, 13.6, 2.1. I left off my 1 there, huh? And then over here be 0.1, right? 0.1 and 0.1 on the other side. So 2.07 is right here, right? So how much of the data is that? Now we can be very exact about this in the coming sections, but right now we can approximate it. We have 13.6 plus 34.1 plus 34.1 plus 13.6 plus 2.1 plus 0.1. We can add all those together, and that can tell us more or less how much of the population we're really dealing with at that point, which works out to be about 98, I think it's 97 point something or another when we add all those values up there, is about 97% of the population. So I put a little squiggly there because we're doing an approximation. You can find that exact value. And I know it's about 97% because when we deal with this section right here, this is 68% of the population. When we deal with this section right here, this was 95% of the population, right? So then we're adding 2 on top of that, and we're adding another 1 to that. So this is just over 97, 98% of the population that we're dealing with here. 97.5, I think, is actually what it works out to be. So when we say that this person right here has a z-value of 2.07, that equates to being taller than 97, almost 98% of the population, okay? Which is a pretty good piece of information to know. This individual is taller than most people in the population. That's neither good nor bad. That's just a thing, right? So what else can we discover here? Okay, well, let's do the other person, right? So the other person was this negative 1.5, and that would be right about there, right? So in that case, how much of the population is that individual taller than? Well, we just simply add up those pieces. So we have the 0.1 plus the 2.1 plus, well, that's not exactly half of that, but we could estimate. Let's just say it's 6. And then keep in mind that's a really loose estimate. It's probably a lot less than 6, and that means that this is what is that? About 8, approximately 8.2-ish. Okay, so this individual is approximately taller than 8.2% of the population. All right. Now some of you may say, "Oh, that's kind of interesting. That's kind of cool." And I agree. It is. How is it useful? Don't know. But what we're doing here is we're just kind of investigating. We're figuring out data here. The whole point of most of what we're doing here with these distributions is just trying to figure out some way to manage and manipulate the data so we can talk about one data set with another or to learn more about that one data set. Now, another way to look at this is we could also say that 97% of the population is shorter, or this individual is taller than 97% of the population. And this person down here is taller than 8.2% of the population. Now, this is the thing. We can also look at this in the exact opposite realm. Since we know that this value, we know this person is also shorter. This person up here. Okay, I'm going to put that right there. The one we just found right there, this person is shorter than roughly 3% of the population. And down here with this one, this individual is shorter than, what does that be, 91.8% of the population. Okay. So that's actually pretty good information to know. So height-wise, height really, in my opinion, doesn't really make a huge difference unless you need a particular height for a particular event. Like, for instance, we're talking about basketball players. In general, height is useful when you're playing basketball. So if you have an individual who is 60 inches tall and wants to become a professional female basketball player, even within the female population, that individual is shorter than almost 92% of the population. And then you move that into the realm of basketball players, and they're probably shorter than almost all of the basketball players. I bet you find very few professional women's basketball players that are 5 feet tall, as opposed to someone who's 5'10". Well, 5'10" is shorter than only 3% of the population. And they're taller than 97% of the population, which means that their odds of being taller on the basketball court would probably be pretty good still. And I bet if we looked at the WNBA, we'd probably find that to be fairly true, that 5'10" is not necessarily unusual height within women's basketball. Men's basketball, I bet you find that 5'10" is actually pretty short, as males are normally taller than females. Okay, so there's a lot of information we can start talking about with this. If you're in reference to sports, maybe you are referring to pilots. If you're talking about a military pilot, there's actually a height limit for military pilots, and it has to do with legitimate issues with some of the individual fitting inside of a standard cockpit. And they also have to be over a certain height because, again, they had to fit inside of a standard cockpit size without any modifications. So those pilots have to fit within a certain realm. So if we found that this individual was 2 standard deviations above the mean, maybe that means we can't use them. And that'd be useful information because they're just too tall to fit inside of that equipment that was designed for someone who was an average height of 64 inches. And that is true across the board. When you look at a lot of equipment, airplanes, cars, a lot of times it's actually designed, a lot of times those events are actually designed around men's heights, and they've said the men's height is whatever this value is, and if we let it vary by this much, the standard deviation is this quantity, and then we can design the car around that idea. Maybe we say we want it to be a z-score less than or equal to 2, meaning whatever this value is that we end up doing here, we want to be able to stay within 2 standard deviations because that's going to take care of 95% of our population. What does the height requirement for that car need to be, or to accommodate the long legs and the long torso for individuals? I've actually heard someone say, well, tall individuals will typically go for SUVs because they fit into the vehicles better. And that there's some evidence to that, but there's also ways that smaller cars can do the same thing. As a lot of times, even small cars are designed with the idea of being able to fit 95% of the population, which means they're looking to contain or wanting that z-score, the absolute value of that z-score, to be within 2 standard deviations, or less than or equal to 2, which means that they would contain 95% of the population. All right, so I hope this was useful. Please reach out with questions and comments, and I will try to make additional videos as requested. Thank you. Have a great day.